All right, so we'll start chapter 17 here. We've looked at what constitutes an aromatic compound, how we can look at a compound and count its pi electrons, and look at the hybridization of its atoms to determine whether it's aromatic or not. And so now we're going to look at some of the reactions that aromatic compounds undergo. And we looked at a lot of different kinds of aromatic compounds in the last chapter, heterocyclic aromatic compounds that had nitrogen and oxygen and sulfur. We're not going to get into the reactions of those compounds. We're only going to look at the reactions of benzene. It's going to be our prototypical aromatic compound, and we're going to see how the reactions that benzene undergoes are different than we would expect for a compound that has double bonds. We are familiar with the chemistry of alkenes, and so we'll see that even though benzene is essentially composed of 3 alkenes, it has different chemistry than alkenes. And so it gets its own functional group that we call aromatic. Okay, so one of the important reactions that aromatic compounds undergo is called aromatic substitution. And there are 2 kinds of aromatic substitution. Sorry, my computer just had a pop-up. There are 2 kinds of aromatic substitution. There's electrophilic aromatic substitution and nucleophilic aromatic substitution. And so we'll look at electrophilic aromatic substitution too. And so this name is always kind of difficult to interpret. So when you look at some of these names in chemistry, and so in any reaction that involves electrophile, there's also a nucleophile involved, right? There's always, if there's an electrophile, there is a nucleophile. If there's an acid, then there's a base. If there is an acid-base reaction, right? If there's one, then there has to be the other. Like, reduction doesn't occur without oxidation. And so when we say electrophilic aromatic substitution, we have to indicate which of the partners in the reaction we're referring to. And so counterintuitively, when we say electrophilic aromatic substitution, benzene is actually being a nucleophile in this case. So the electrophilic aromatic substitution is referring to benzene reacting with an electrophile. So we're substituting an electrophile on the ring. And so that's why it's electrophilic aromatic substitution, because the group that gets substituted onto the ring is an electrophile. But benzene itself is actually reacting as a nucleophile in this reaction. And so we will briefly talk about nucleophilic aromatic substitution, in which benzene is reacting as an electrophile, and it's reacting with a nucleophile in that case. And so when you see these reaction terms referred to as written as this, electrophilic and nucleophilic aromatic substitution, just remember that for me anyway, it always seems counterintuitive, that I always want the electrophile to be the benzene ring or the nucleophile to be the benzene ring, but it's actually the other partner in this reaction that the name is referring to. And so if we look down below, what we can see is that we have a benzene ring, on this case an alkyl benzene with an R group, an unspecified R group, let's just call it methyl, for example. And if we react this methyl benzene, remember the common name is toluene. If we react this toluene with nitric acid and sulfuric acid, we can put a nitrate group onto the benzene ring. But this is a regiospecific reaction, and so the nitrate group goes in a specific position relative to the methyl group. It goes in the 1,4 position, which remember we called para, or it goes in the 1,2 position, which we called ortho. And I should say it's not or, it's and. It's both para and ortho. It does both. I guess it does depend on the nature of R. If it was a methyl group like we had specified, then it would be ortho and para. But what we don't see is meta. We don't see the 1,3 substitution pattern. In this reaction, it's 1,2 substitution, ortho, or 1,4 para, but it's not 1,3. So it's not meta in this case. And so this is that's the regiospecificity of this particular reaction. And notice what's happened is there was a hydrogen atom at the position where now there is a nitro group. So that nitro group, NO2, replaced a hydrogen, or it substituted a hydrogen atom, and the the aromatic ring attacked it. So the aromatic ring attacks an electrophile, which we call E+. That's the little green E+ down there in the bottom series. And it replaces a hydrogen atom. It substitutes a hydrogen atom. So that's where it gets this name, electrophilic aromatic substitution. And so this is different than what we would expect for an alkene, because remember what an alkene would do if it were reacting with an electrophile. Alkenes can also serve as nucleophiles in a similar sense as what we're seeing here. But remember what happens with an alkene is when it reacts with an electrophile, the double bond doesn't reform. The double bond grabs two bromines, for example, and we get a dibromination across an alkene. And so we can put groups across an alkene in a similar fashion, but we don't reform the double bond at the end of the reaction. Look what happens here. In the first step, the aromatic ring, the aromatic electrons grab an electrophile, which we would say that's really odd, because we just in the last chapter talked about how aromatic electrons are very stable and they're very unlikely to disrupt the aromatic system. Any reaction that's going to disrupt the aromatic system is unlikely to occur. And that's absolutely true. And so we have to put in some pretty harsh conditions for this reaction to occur, because benzene is very stable. So we have to react it with something that's very reactive in order to get benzene or some aromatic system to use its electrons as a nucleophile. But in this case, that's what it does. We have a very strong electrophile. So the aromatic electrons serve as a nucleophile, and they grab that electrophile, which adds to one of the atoms in the ring. We get to that intermediate that they're calling the sigma complex there. And that sigma complex, it has a lot of resonance structures because there's still two double bonds left in the ring. And look at the last step. There's a base that takes the hydrogen where the electrophile is now bonded, and the electrons that are left behind when that hydrogen atom leaves, those electrons reform the aromatic system. So in the first step, the electrons are used to grab the electrophile, and in the last step, the electrons that are now so remember, the electrophile is replacing this hydrogen atom. So look at that atom that will eventually have the electrophile bonded to it, has a hydrogen atom bonded to it first. So on the left side, it's hydrogen. In the intermediate, it's an electrophile and hydrogen. And in the product, it's just electrophile. So we're removing that hydrogen. And so the electrons are used in the first step to grab the electrophile. And in the second step, when the hydrogen leaves, it leaves its electrons behind. And so the aromatic system is disrupted during this reaction, but only for a moment. And then the aromatic system comes back. And so that's what's kind of counterintuitive about the way that these electrons react. Counterintuitive in one sense, which is if we're comparing it to the way that alkenes react, but also it makes sense when we now apply what we understand about aromatic compounds, which is that aromatic systems are very eager to form. And so if a reaction does something to disrupt an aromatic system, there's a very big driving force for that aromatic system to return. And so, yes, it's hard to get the aromatic electrons to react as nucleophiles, but once we do, and we put that group on there, and we've disrupted the aromatic system, it tries very hard, or there is a very large driving force that is pushing that aromatic system to reform. So here is what happens in the first step. One of the double bonds in benzene, it doesn't matter which one, remember they're all equivalent. One of the double bonds is going to grab E. E plus is our electrophile. It's just a general electrophile, and we'll see that the nature of these reactions that we're going to go over in this chapter differ by what E is. E is going to be a different group. And so once the double bond grabs that E and we make this sigma complex, notice that what happens is similar to what happens when a double bond reacts with an electrophile when we looked at alkenes, which is that one atom is going to get, one of the atoms in the double bond is going to make a new bond to that electrophile, but the other atom is going to be a carbocation. And that's what we see here. One of the atoms in that double bond gets bonded to E, but the other atom in that double bond is a carbocation. And now that we formed a carbocation that's conjugated to this pi system, then that carbocation has many resonance structures, and we can see that there's 3 resonance structures here. Now, it's not aromatic or anti-aromatic. This resonance structure, this sigma complex, is non-aromatic. And it's non-aromatic because that atom that is bonded to E and H is sp3 hybridized. So once it grabs that E, it no longer has a p orbital, that atom, and so it is no longer an aromatic or anti-aromatic group. It's non-aromatic at that point. All right, and then this is the full mechanism here. So in the first step, a double bond grabs an electrophile. That electrophile gets bonded to either one atom in the double bond or the other, and the one that didn't make a new bond becomes a carbocation, as we see here. And then in a second step, a base removes a hydrogen atom, the hydrogen atom from that tetrahedral carbon that we just formed, and when it leaves its electrons behind, and that reforms the aromatic system. So what we've done is we replaced that H with E, so it's a substitution, just like an SN2 reaction, right? We've replaced a group with a new group. We have a leaving group, and we have our electrophile, in this case, the group that we're adding. Okay, here is our first specific example. So if we had a double bond and we treated it with Br2, in the product, the double bond would be gone, and I would have 2 new single bonds to bromine atoms. If I treat an aromatic compound like benzene with Br2, all by itself, just Br2, nothing will happen because benzene is too stable. So I have to treat it with a compound, in this case it serves as a Lewis acid. It's iron bromide, iron 3 bromide, and iron 3 bromide can help to activate the Br2 and make it even more reactive than it already was. And so when that happens, now the benzene can react because we have made the reagent very, very reactive, but it doesn't react the same way that a double bond would, because in the end, we have only added 1 bromine atom, we replaced a hydrogen atom with a bromine atom, and although we used the double bond to put the bromine there, the double bond was returned at the end of the mechanism. So it's when I react benzene with Br2, it's a similar but different outcome than if I react an alkene with Br2. So this is a 2-step reaction, like we just went over the general mechanism. We'll go over the specific mechanism here in a minute. So the first step involves benzene and my reactants, my other reactants. In the second step, one of those bromine atoms is added to the benzene ring, and we make our sigma complex with a tetrahedral atom and a carbocation. And in the last step, our base removes that hydrogen atom, which restores the electrons to the aromatic system, and the system becomes aromatic again. And so we have this 2-step mechanism that's overall exothermic, but it has a big endothermic first step, the rate-limiting transition state, that rate-limiting step in the mechanism. So creating that carbocation and getting benzene to react as a nucleophile has a huge activation energy, as we would expect. And so when we look at the reaction coordinate diagram, we can see that first step, getting benzene to do anything, requires a huge amount of energy. But once we have added an atom to benzene, then the next step has a very low activation energy, and it's very, very exothermic, as we would expect, because we're regaining aromaticity. So when the compound gets those electrons back and we remake that aromatic compound, then the aromaticity that we get that stability, that extra stability that we would expect from the aromaticity of the compound. All right, I think we're going to stop there, and we will pick up here on Monday.